Geologist with extensive international experience in landslide investigation, slope stability and geohazard risk assessment. So his work supported infrastructure projects and national hazard management across New Zealand and overseas. So the talk here is Insights into Causes of Landslides Triggered by Cyclone Gabrielle. So, thank you.
Thank you. Hi everyone, my name's Chris. I'm the stand-in for Kerry Leith. Kerry unfortunately snapped his Achilles and couldn't travel, so he's out of action for a few months, which is really painful. My role in the Cyclone Gabrielle work was I led the initial readiness and response phase, the stuff that Murray talked about with the helicopter responses. And then Kerry led the mapping part of it, and then I've been kind of coordinating national development of national landslide forecast and hindcast models using some of the Cyclone Gabrielle data. So what I'm going to do today is I'm going to talk through, I'm going to talk through what the data that we collected and what we did and what we've done with it and some of the insights into the results. It's worth just pointing out that our role is to provide scientific advice to NEMA when requested. We don't have the funding or capacity to work on the ground with lots of councils across the country, which is a real shame. We'd love to, but we are limited in the amount of money that we have and the amount of people that we have. So we do not do the same things as the local geotechnical consultants. Our role really is to try to get a regional appraisal of the level of impacts quickly to provide that information to the central government and lifeline infrastructure providers and from central government to CDEM groups. If anybody's really interested to read in detail what our role is, have a look at our response to the Cyclone Gabrielle coroner inquest. So before the rain made landfall, we had a bit of a heads up from our colleagues NEWA to tell us that there was a major event coming, and we'd serendipitously generated a landslide forecast model for Northland and Auckland region. So we had that set up to run pretty much automated. So we ran a couple of forecasts about 48 hours out before the rain made landfall using the NZCSM rainfall model. And that gave us a bit of a heads up with regards to kind of the likely severity of what was likely to come. And I'll talk a bit about that, but then I'll kind of work through the different things that we did and then look at the main kind of results that we've got so far. It was a massive team effort. There was a lot of people involved, Inaki Whenua, University of Canterbury, various other parties at different stages along the way. The different project phases, Murray nicely talked about some of them, and no, I wouldn't get annoyed with you, it's fine. But I will bust a few myths, though, if that's all right. So our first phase was the response, so this was forecasting and getting out in the helicopters. Now, we're not just concerned with Hawke's Bay and Tairāwhiti, Auckland got nailed as well. Over 300 homes in Auckland were bought out by the council because the risk to life was deemed to be too high. There were several deaths in Auckland as well from landslides. There were over 2,000 properties that were impacted by landslides alone, let alone flooding in the Auckland region. So our interest is not just Tairāwhiti, Hawke's Bay, it's the entire country, and Cyclone Gabrielle affected pretty much the entire North Island, all the way from Northland down to Wairarapa. And so it's our role to try to get out there and get the teams out there to get that information to central government as quickly as we can. And so we work directly with the regions where we had contact, but like I said, through NEMA is our main area. So the first things we did is we provided impact forecasts, because just providing landslide probability maps is not that useful. So we turned these into impact forecasts. This is the first time we've done it in New Zealand for landslides, and it showed us the scale of the event. These are quite useful because we've been out to the various people we provided them to after to say how useful were they, how correct were they, and we're going through validation exercise. There might be people in the room that have been asked about this, I don't know, but the 32 end users, next users, were asked to provide feedback across the various sectors who used them. And then as the project developed, so the initial work was funded through redirection of our internal funding. We don't get any new funding for response initially. We redirect our own through the GeoNet project. And then as things started to settle down with regards to people getting more and more involved, central government put up 1.4 million, which is not a lot of money, but it helped us at least start some of the mapping work, which Murray talked about, and I'll talk about that in a minute. And then since then, we've been doing quite a lot of work for various people around the place using some of those data sets and collating other data sets. So these are the kind of impact forecasts that we did, mainly focusing on homes, roads and rail across the region. And like I say, now we've done them, we can validate them based on the actual impact. So we have a couple of PhD projects at University of Auckland, University and Canterbury that are doing these. We got up pretty quickly in the helicopters. We had 6 teams, and the idea was to capture as quickly as we could the focusing on lifeline infrastructure and where people were and where people had posted on social media, just to try to get an area and understand where things were bad across the region. Like I say, from Northland all the way down to the Wairarapa, we had 6 or 5 teams in helicopters. And we provided that information in near real time to NEMA and anybody else. So as your people are mapping in the helicopter, it's being seen live on people's dashboards, wherever they are, if you had access. We then were requested to start mapping. And the idea with the mapping was we reached out to the infrastructure providers and local and regional councils and others and said, give us the priority areas where you want us to map. It was never our intent to map the entire landslide distribution from this event. A, we didn't have enough money, and B, we don't have the resources to do it. And we'd still be mapping it now, as Murray's talking about. We just can't do that. It's not in our kind of remit, response and that recovery stage. So we asked people where they wanted us to map. They gave us their results, and we had high priority, which is where people and lifeline infrastructure were exposed. Can I just make a point? This wasn't us. This is other people telling us where they want us to map. Then moderate priority, low priority, and scientific interest. The scientific interest is us, where we've said we can't just map the high priority areas. We've got to get a representative sample around the other regions just to fill in the gaps, because we can't just focus everything on those areas. We need to see what's happened in other regions, including areas that didn't have any landslides, because they're just as important as areas that did have landslides, especially when you've got the rain data. The mapping was done by 25 experienced mappers, and with Manaki Whenua, ourselves, various other people providing a QA. It was all online and made available 3 times a week. It was put on AGOL updated. So the councils did have access. We have a list of over 70 people who had AGOL accounts in the councils around the country that accessed that. We have the actual dates that they were accessed and who accessed the data. So we know people used or at least accessed the data as it was being collected. So the idea was that it went up as quickly as we could, but then that was raw, and then we had to then put up data that had been validated. The validation took longer because we have to do it. It needs to take a bit of time, goes through the QA process. So this was the kind of mapping approach. We created a live document that was again online that people could access. The report was a live report. It was done online so people could actually access that report. And it's still live now. It hasn't been finalized because the QA and things are still going on some of the data sets, especially, as Murray mentioned earlier, the Earth Scanner data. I have no idea who decided to purchase Earth Scanner. It wasn't us, but we've had a nightmare with it, and we've ended up, like I say, we don't really use it, to be honest. We've tried to move the data, but it's just so bad. And the problem is the georectification and the orthorectification of it is it's just not good. And you can't get the original data files to help with that, so it's really difficult to use. We decided to map points and lines. We did a whole test of, do we map polygons, do we map points. So we mapped points and lines to represent the debris trails. We did a whole testing approach, and we came down to the most efficient and effective way to capture as much data as we could was to do attributed source points. So a point in the middle of the source area and then a line showing the debris where it went. So this is kind of like a typical example of what it looked like. And this kind of gave us the number of landslides in the priority mapping areas. It gave us the type, the area, the run-out, source volume, because we can estimate that from differencing of LiDAR models after the event. So the reason I've got asterisks there is because it's kind of a secondary stage of data acquisition. Travel height and travel angle. So like I say, the data was provided raw, updated 3 times a week initially, and then it just dropped off as we got through it. And then QA, the reviewed data, was provided. There's a version 1 and a version 2 data set available now. The version 1 data is everything mapped, with the original Earth scanner mapping included. Version 2 is where we've moved the landslides that were mapped on Earth scanner to where they should be. So there's 2 different data sets. They contain 170,000 landslides in total. Quite a bit of work was done, back then to look at with Dragonfly, who they're a data science company, to look at sentinel differencing. And we used that to compare against the landslide distributions that we'd mapped. And you can see they work kind of well, but they're essentially 30% of the map sources were missed in the area, in the priority mapping grid cells that we mapped. And most of the 65% of the slides that were missed were house or size or smaller, which is not surprising given Sentinel's quite a large resolution. But it just shows the usefulness of hand mapping. So this is the kind of products and outputs that Kerry and team have been generating, which is kind of the source areas, the debris trails, and then using them for run-out modelling. And this data set's being combined with other data sets that we have around New Zealand from historical storm events, but across the whole country, to generate landslide models that we can use to forecast landslide occurrence in future events, but also the run-out component, looking at where the debris went and where the sediment goes, is another important component that is also part of a current endeavour programme called Sliding Lands. And if people are interested in that, please come and have a chat with me at lunchtime. I can point you in the right direction. So we use the landslide distribution. So these are the priority mapping grid cells on the left that we mapped across the country. The NIWA rain is there. NIWA soil moisture is there as well. And we used these areas to then train some models to really look at the regional scale effects of various susceptibility and forcing factors on the actual landslide distribution that we'd mapped. So just some photographs of some of the landslides we visited, both in the air and in the field, to try to get some of the relationships between the landslide occurrence and what we actually saw, to validate some of the data sets, again, across the country. So I'm focusing in here because in Hawke's Bay, Tairāwhiti region, because this is obviously an area of interest for everybody here. And I've left out Auckland, even though we've got similar results for Auckland. So what we're looking at here is just the main factors that might control landslide occurrence, and we're looking at it at a broad scale. So we've got the geology, which is QMAP, so it's not the best geological mapping, but it's available for the whole country, and that's where we're trying to get at. We're not trying to use data sets that are incomplete or just localized for one area. We want to try to develop models that can be used consistently across the country, hence why we're using QMAP. We're using the land cover database, so the Manaaki Whenua LCDB5, and then the SMAP soil depth. Again, it's a bit sporadic, but at least it's available for most of the country. Obviously, a lot of these have problems, they're issues, but again, it's that regional scale view that we're trying to capture. The other regional factors that we're trying to capture are what we call morphometric. So these are things like using the LiDAR DEM, thank you, and the derivative products from the LiDAR DEM. And so we look at all these, but we look at all these with the landslides. And please don't try to read these. I've got a link to the paper, and through the paper there's a series of other reports and papers that can be used to get this information. But what we're doing here is we're really just looking at what's controlling the landslide distribution, trying to tease it out before we go down a machine learning approach, right? So my background is rock mechanics and soil mechanics. I'm coming at this from a mechanics perspective. What regional factors control landslides, not throwing them in a black box and trying to hope for the best, actually try to understand the controls, but again at that regional scale. But some of the data sets that we were able to get access to, things like the vegetation loss data set, so we can start looking at, well, where did the landslides occur? So anything like the higher peaks show you where things correlate quite nicely. So essentially we're saying here, between 4 and 5 years before Cyclone Gabrielle, vegetation was lost, then that's where landslides tend to occur. And then this is pretty much my last slide, which is about the comparison of the mapped and simulated landslides. So we've mapped these areas, we've simulated them, and then we can then go out and then we can do a blind testing now. We can map other areas and see how well the models perform and then update the models. So the idea here is that we're generating nationally consistent landslide forecast models. Yeah, they won't tell you where landslides will occur on the ground with high precision, but they'll capture the scale of the event in future rain events. And earthquakes, actually, because we have an earthquake models too. Thank you. The end.